Good afternoon, everyone. Thank you for joining us today for the award ceremony and for the Distinguished Scientist Fellow and their lecture. I would like to introduce Dr. Kristin Persson from Berkeley National Laboratory. For those of you who don't know me, I'm Linda Horton. I'm the Associate Deputy Director for Science Programs in the Office of Science in the Department of Energy, and I will be the moderator for today's event. Joining us today is Andy Schwartz, who is the Acting Associate Director for Basic Energy Sciences, as well as online DOE National Laboratory Directors, the nomination teams for this prestigious award, the peer reviewers, and of course, our fellow is here, and I'm sure her family is online to listen to her lecture. To begin our program, we have recorded remarks from the Berkeley National Laboratory Director, Dr. Michael Witherell.
Hello, I'm Mike Witherell, the Director of Berkeley National Laboratory. I know I speak for all of us here in the lab community when I say how proud we are of Kirstin and her work. And we're so pleased that she has been honored with this distinguished fellowship. I first met Kirstin when I came to the lab as director and was struck by her passion for accelerating the rate at which we discover and exploit new materials. In addition, she had the ability to communicate the need for faster materials discovery and to demonstrate how it could be done. We at Berkeley Lab have long recognized the importance of her visionary materials project. In 2009, Paul Alvasados allocated funding from the laboratory-directed research and development program to start building the project's capabilities. Her vision aligned very well with our public service mission to make an easily accessible database of materials properties so it could serve the diverse community of material scientists. Just 2 years after that, Kirstin and her team launched the materials project to the public, and it is now the most widely used open access repository of information on inorganic materials anywhere in the world. The interdisciplinary nature of the project, combining domain knowledge, high-performance computing, and modern data infrastructure, is really perfectly suited for one of the Office of Science's national labs. We are committed to building and operating collaborative long-term teams who are committed to advancing science and technology. Thank you to the Office of Science for recognizing Kirstin's very impressive work over the years that have helped to advance the nation's effort to accelerate the design and development of new materials for energy applications and many other important fields.
Thank you, Mike, for those wonderful remarks about a wonderful person. One of the aspects of today's ceremony is recognizing how extremely important it is to recognize the impact of research supported by the Office of Science. A special joy is celebrating the people whose careers have led to these great accomplishments. Today's awardee especially highlights innovation at the interface between the office's missions in fundamental discovery-driven science and use-inspired energy research. It's just marvelous. On August 12th, DOE announced 4 national laboratory scientists as the 2024 DOE Office of Science Distinguished Scientist Fellows. Those were Dr. Mary Bishai from Brookhaven National Laboratory, Dr. Lois Perfman McInnes of Argonne National Laboratory, Dr. Kristin Persson from Berkeley National Laboratory, and Dr. Jerry Tuskin of Oak Ridge National Laboratory. Today's event is the first lecture in a 4-part seminar series featuring the 2024 Distinguished Scientist Fellows and, of course, honors Kirstin. Dr. Persson is the Daniel M. Tulloch Distinguished Professor in Material Sciences and Engineering at UC Berkeley, a faculty scientist at Berkeley National Laboratory, the director of the Materials Project that I'm sure we're going to hear a lot more about today, and until very recently, the director of the Molecular Foundry, one of BES's science user facilities. Before I present the award plaque and we hear from Dr. Persson, I'd like to say a few words about the program and how we arrived at the 2024 cohort of attendees. The Office of Science has honored 17 fellows, including the 2024 group, since this program started in 2019. The awards honor the extraordinary scientific achievements and professional service records of senior scientists at the national laboratories. Each fellow receives $1 million in direct funding to be used to support activities that develop, sustain, and promote excellence at the Office of Science's research through collaboration between institutions of higher education and national laboratories. Nominations were solicited from all 17 of the DOE National Laboratories, with the nominees all endorsed by their lab director. But for those of us that used to work at national laboratories, we know how special that is. The selection of fellows is based upon a rigorous internal and external review process. Each fellow represents excellence in their field and joins the growing community of fellows who represent the best of what DOE laboratories have to offer in science, mentorship, and service. Now it's time to honor today's speaker. Dr. Persson is being honored for her leadership and influential contributions to materials science through pioneering data-driven approaches to accelerate clean energy innovation in materials for energy storage and solar fuels. She has demonstrated exceptional leadership in creating and managing large and complex research programs, most recently serving 4 years as the director of Foundry. And since 2011, she has served as the founding director of the Materials Project, an extensive database coupled with powerful analytical tools that is available. The data is available free of charge to anyone who logs into the resource. It's one of our pure databases for the Office of Science. The Materials Project demonstrates the visionary talents of Kristin. She saw a need, rose to the challenge of meeting that need, and developed an amazing resource for the community. The goal of the Materials Project is to use computational tools to drastically reduce the time needed to identify new materials with the desired properties and applications by focusing costly time-consuming experiments on compounds that show the most promise computationally. Dr. Persson has established a multi-institutional, multinational effort to compute the properties of inorganic materials and provide data and associated algorithms to materials researchers. To give you a sense of the impact, the Materials Project is probably the most widely used open access repository of information on inorganic materials in the world. The database includes millions of properties on hundreds of thousands of crystalline structures and molecules. More than 500,000 people from across the world are registered as users, and really impressively, an additional new 300 users sign up nearly every day. It's really amazing. She has made tremendous contributions to science, published hundreds of scientific papers with over 40,000 citations. She's been recognized by her peers through fellowships, honors, awards, and professional positions, too many to really list here. For the Office of Science, her collaborations have extended to multiple energy frontier research centers and both of the Office of Science's energy innovation hubs. She also embodies a strong commitment to improving diversity, equity, and inclusion at Berkeley, UC Berkeley, and more broadly across the field of computational materials sciences. Her level of service to the community and future generations of scientists is truly inspiring. She has mentored many students and postdocs and served on governing committees focused on inclusion properties. Her work through the Materials Project has helped level the playing fields in countries where access to expensive instrumentation and computational tools can be challenging. She represents the attributes of an Office of Science Distinguished Scientist Fellow. She has commitment to science, leadership, and service. Her leadership, managing complex scientific challenges and discovering solution and commitments to service is why we are so pleased to honor her today. So the next step is to actually present the award. So I'd like to invite Andy Schwartz, again, the Acting Director for Basic Energy Sciences, to do the presentation. If you would join us, please, Kirstin. It is our pleasure to present this award to Dr. Kristin Persson for her pioneering advancements in data-driven materials, design, and discovery through first principles-based computations and analysis algorithms that yield materials with optimal properties for engineers and scientists worldwide to accelerate innovation, and for her management and outreach skills that promote DOE's mission. Congratulations. One more picture. Yes. Thank you. Thank you. Okay. I knew we had too many pages so fast. All right, at this point, please join me in welcoming Kristin Persson for her lecture, Fueling the Data Revolution in Materials Science, which will be followed by Q&A, which I think is the best part of the program, by the way, although the lectures are really interesting too. So thank you, Kristin.
Thanks, Linda. Thank you so much. I am tremendously honored and humbled at this award, and it's really my privilege today and to talk about the things that indeed, as Mike said, I'm very passionate about. So I'd like to frame my talk in terms of the 4 paradigms of science. It has been proposed that we have 4 stages. The first one being empirical science, where we observe things in nature, and if those observations are fairly consistent, and if we have a mathematical framework, we can cast those observations into equations, and we may not have to observe them every single time. Now, some of those equations can be difficult to solve manually. So when we get computers, we can solve those equations, and that enables a third paradigm of science. Now, if we have enough data, either by empirical science, by experiments, or by the simulations enabled by the third paradigm, we unlock the 4th paradigm of science. So we use the data itself to predict the physical nature of processes, of behavior. And if that data is consistent, diverse, robust, and curated enough, that builds the background for doing advanced science or unlocking new ways of science. And timely, just about a week and a half ago, it was announced that both the physics and the chemistry Nobel Prizes of 2024 indeed recognize this 4th paradigm of science. Specifically, if I focus on the chemistry one, the remarkable accuracy of AlphaFold to predict the structure of proteins is an achievement due to the algorithms that were developed. But I would also like to give a shout out to the collection and the curation of the systematic data that underlie the training of these algorithms. So the AlphaFold architecture was trained to high accuracy using only supervised learning on the protein data bank data and increased accuracy obtained from UniClust 30. So a little bit of history here. In 1971, the protein data bank was established at Brookhaven National Laboratory by Walter Hamilton, and there have been many directors since. In 2003, the Worldwide Protein Data Bank was established as a single global archive of macromolecular structural data. And as somebody who every day deals with the aggregation, the curation, the processing, and delivering of data, I know how much work this is. And this is what they're doing, depositing, data processing, and distribution centers. And this underlines the effort of these two Nobel Prizes, enables them. I'm also joined, this is recent from the last, I believe, couple of months, in the AI companies that I think we hear daily from in papers and journals and news, are calling out the need for data, to focus on the fuel of machine learning as much as on the algorithmic development. They're also calling out the fact that because we're now realizing that when we give data in the public domain, it may be coming with privacy issues. So more and more data is locked up behind those kinds of walls, and that troubles people who thrive on the openness of data. And that's something to think about in terms of science. If we want to unlock the fourth paradigm of science through scientific data, where should that data rely? We have control over it, accessible to people. And this is the picture I show my students, because all of my students who come to UC Berkeley, by and large, 95% of them, when I ask them what they want to do, they say, I want to do machine learning for material science. And I said, wonderful, you want to drive that Ferrari. I get that. But in order to drive that Ferrari, you're going to need to produce the fuel. That's going to take you longer. So producing, curating, featurizing that data is going to take you more time and be probably quite boring compared to the actual training of the machine learning model. And that's the exciting part when you started seeing the predictions coming out of that. So starting out with that and grounding it a little bit, I found has helped with achieving the persistence needed. So taking a step back and looking at material science and a little bit of a personal sort of reflection on where we have been and where we're going. When I was a graduate student in Stockholm in the mid-90s, and if I wanted good curated data from materials, I went to Landholt and Bernstein. Those were my trusted books, where I knew that if I got an elastic tensor out of those books, it was a rigorous benchmark for my computational modeling. And then, of course, you can go to the open literature or the scientific literature. And today, in those days, we didn't have text mining tools. Today, we have text mining tools. But even if you use text mining tools and go to Landholt and Bernstein, if you look at fundamental material properties, such as the elastic tensor, the dielectric tensor, it's hard to find more than a couple of hundred well-established curated data points. And we have over somewhere between 100,000 to 200,000 unique organic materials that are characterized by the structure. But these fundamental properties have only been measured for a few hundred. So there's no way we can couple through machine learning the property to the underlying crystal structure and the chemistry using that amount of data. It's too little. If you go to something like superconductivity, it looks a bit better. And I would venture a guess, and this is my opinion, that because the superconductivity conducting temperature, if you measure a high one, then you have made a discovery, and that's more highly valued traditionally in our community than just measuring another elastic tensor, dielectric tensor. So there we are a little bit better off. Now, early 2000s comes to the rescue here. Density functional theory, which also got a Nobel Prize. I was in Stockholm at the time when that happened. Was a surprisingly robust way of calculating materials properties. And then it took a while for the computers to get to the point, but in the early 2000s, we could do so-called high throughput computing. We could spit out these calculations on many different nodes on our supercomputer, and we can now calculate many of these properties that are hard to measure accurately, tiresome, and doesn't have a lot of rewards associated with it much more rapidly. So that's another tool in our toolbox. And the third paradigm, right, of material science. So 1996, I was a graduate student in Stockholm. It took me an entire year to produce those photon dispersion curves that you see over there for just one element, tungsten, because I had to fit the pseudopotentials myself. I had to parallelize the plane wave code. And this is a lesson for my students again, who do all of those things beautifully now for free in a few seconds. But that difference between 1996 and 2024, and we are today, is rather remarkable. That's a paradigm change in terms of the ability to produce really remarkably accurate, or at least systematically accurate data for materials. So on the materials project today, we have, as Linda mentioned, over 150,000 materials, but also more importantly, millions of calculated properties. And we now can correlate back to their crystal structure and their chemistry and do accelerated learning. So we don't have to compute everything. So the idea here is, of course, that we are going to move on from an Edisonian approach, which is from a paper in Scientific American where they nicely graphed this for us. This Edisonian approach that you sort of have an inspiration, you try to make a material, you test it for the properties that you want, and you keep iterating until you found the material that fits your purpose or application. And now we can use our computers or our databases to pre-filter or to scan the periodic system, scan the number of chemistries and structures that are out there, and see which ones are particularly good for the kind of properties that we want, and sort of list those properties. And we can give a lower number of candidate structures to our experimentalists, and we can then iterate together and sort of focus them on the ones that have a higher likelihood of making it. And this is, of course, named after Thomas Edison, and I named the latter one after Tony Stark in Iron Man, because if you remember, he picks out those cool sounding elements in Jarvis, his computer, he synthesizes it in his hands. It all takes about 30 seconds. He also tests for biocompatibility. We're not quite at Tony Stark yet. I'm hoping to get there, but that's the dream. Okay, so usually when I give this talk, people go like, well, have you actually seen an example of a material that was computationally designed and has actually made it? So here's my one example, and I'm proud to have been part of it. When I was at MIT, we were enlisted by Duracell to come up with a better alkaline cathode for their non-rechargeable batteries. And they gave us $1 million in a year to do it. And we wrote the first sort of set of scripts to calculate on their computer the number of things that we knew how to calculate: voltage, capacity, energy density, and even stability, which turned out to be actually the real bottleneck. Because these little guys sit in an electrolyte of pH 15. So most of the materials that you would consider would corrode pretty badly. We screened over 100,000 compounds for them. 1,500 made it on energy criteria, which you would think is the most important for a battery cathode, but it turns out that the stability criteria down here was actually the real killer. So only 200 compounds were even remotely stable under those conditions. After a year, we gave 200 compounds to Duracell, and in 2019, I was at the launch in Austin, where they launched a new brand of alkaline cathodes, where they're now blending in, as you can see here, 200% extra life. So I know for a fact that the material we found was 2 times better than manganese dioxide, which is what they had before. It did take them 10 years, so from the time the computations worked or they got the list to actually commercialize it. So that still talks about how much time it takes to bring a material all the way to market. Okay, so a little bit more of the sort of perspective here. Linda mentioned that I started this at LBNL. So I came with that vision to LBNL. I was really excited about what computations can do for accelerated materials design. So in 2010, I wrote this LDRD that I called Accelerated Materials Design Through First Principles Calculation. It was a little bit of a mouthful, right? So Materials Project sounds better. That was the second version generation. But I did have the little old iPhone here. Like, you're supposed to have this in your pocket. It's supposed to be easily accessible. And Jay Kiesling and somebody else, I think, gave us a prize for mobility competition. So these are all very early, but it was important, that LDRD, because it set us up for the next round of funding that was announced through the Materials Genome Initiative. So we founded the Materials Project in collaboration with MIT and other partners at LBNL in 2011. And we were supported as one of the 5, I believe, inaugural software centers that came through the MGI, and we were included as an MSD program in 2017. And these 3 things that are here that we promised to do: we promised to accelerate materials discovery through development of advanced scientific methodologies and scale those computations over available infrastructure, employ data-driven predictions, and disseminate that data for free to the public. Those 3 things are still the same as they were in 2011 when we wrote the proposal. And I'll very briefly touch upon these 4 pillars. The first thing I'm going to say a little bit about, because most people underestimate the amount of work it takes to do this on the software infrastructure and data infrastructure part. It is truly the tip of the iceberg when you log on to the materials project and you see all the compounds, you can filter through it. The amount of work that goes on underneath is not to be underestimated. So I wanted to give a shout out to that, and particularly the software engineers, that this is their daily 24/7 job to monitor this. So here are the codes that we have in-house developed, and I call them metaware because they're not really the codes that solve the Schrödinger equation. Those other people thankfully have done somewhere else and keep improving on, but all the codes that manage the computations, the input output, the organization, the curation, the dissemination, the checking of everything, the API, all of those codes we wrote in-house and we continuously improve upon. So this is not something that you've written it, you move on. It's like your Microsoft from 2010, you can't even use it anymore, right? So you have, these are not static things, they are continuously updated. And then we have a number of community codes that as the material project keeps getting more and more part of everybody's work life or like engineering life, more and more people add on codes that either operate together or with these codes. So it's becoming a community. We learned best practices from industry and other software developers. We made everything open source, which in the beginning was also a bit of a question mark. Should everything be open source? It's hard to manage. You're giving away everything for free, right? Your hard-earned work. It has really paid off. We now have over 250 active developers of many of our codes that help us not just to develop new directions, but also find bugs and help us with consistency. We have some tremendous people that devote their evenings and weekends to checking all of the different changes to the code. So every single addition to the main branches get checked by these folks. And I'm forever indebted to all their work. Everything comes with clear documentation and we continuously test everything, and trust me, everything breaks also all the time. We have weekly meetings just on the software infrastructure alone. Here's a snapshot of what the builders look like. So if we have new data being calculated, for example, at NERSC on a new material, then that material's properties gets propagated into all of these different buckets. So to zoom in here, here's the dielectric builder, the oxidation state builder, the piezoelectric builder, the magnetic builder. So one single material now gets parsed into, oh, what kind of properties does it have? Does it have this magnetic state? Does it have this density of states? Does it have anything else associated with it? And all these things have to be done automatically. So all of this is software infrastructure, and it really provides provenance. It's completely open source. Anyone can go in and look and check to see that we did it the right way, and we can go back and see if it's consistent what's been done before. Something that people tend to get surprised about is that most of the things in the materials project are not from what we calculated in 2011 has been recalculated because DFT gets better. We get faster computers. So whenever we can do something better, when we feel like we're not quite state of the art anymore, at least in high throughput, then we recalculate it. And that's also the sign of something that isn't static. It's a living organism that keeps getting better and better and encompasses more and more knowledge. We also have this documented and robust deprecation process that when old data is replaced, it doesn't get deleted. We save it because either people want to learn from it, or because somebody may have actually published a paper which included that data. It may not have been wrong, but there's a better data point out there now. So that's important for knowledge transfer and provenance. So if I were to sort of give a snapshot of the whole materials project infrastructure in terms of software and data structure, this is it. These are our own codes that we developed. We integrate with NERSC and production. We save in MongoDB. We check our codes via GitHub. We're open source, but we also partner more and more with the cloud. So we used to disseminate the interior materials project from NERSC. That was not optimal because NERSC is not set up to be a data provider, but AWS is. So now we have a good partnership with AWS such that we are open 24/7. We have every single one of our materials tagged by DOI, thanks to OSTI and the pipeline to OSTI. We have Datadog partnership, Docker partnerships, and all these things help us to really keep a robust, efficient, timely resource for the community. So that was that on the infrastructure and data. So what people mostly want to see is just what does it do for materials and what does it do for the community? So I'll give a few examples. You've already heard about the Duracell one. Here are some materials that we have predicted in-house and that would then subsequently synthesize and tested and shown to work with the functionality that we intended them for, or we had screened them for carbon capture, from magnetocalorics, thermoelectrics, photocatalysts, and some others. And I think the important part here is that there's a breadth of different materials, but the actual properties that we screened on are very much similar properties. And that means that saving them and keeping them for other things is a sort of a leveraging of the same data. So it's not like you have to redo the database. In many cases, it's stability. It's various derivatives of the energy that's important. And though all of those can be redone for other applications, so this is a time saver in terms of saving the data for other endeavors. I'll give one specific deep dive. And here I really want to thank John Gregoire and Jeff Neaton as well, because they were part of the team in the first round of JCAP, when we were tasked with finding new solar fuels or catalysts, photocatalysts for solar fuels. So when I was brought in, not in the beginning of JCAP, but a few years in, this was the state of the art. And if we had to find a new photoanode, we wanted a valence band maximum with the right energy for oxygen evolution. We wanted a band gap that had the right band to absorb efficiently visible light. And maybe surprisingly, the third criteria here, and again, the killer, stability in the operating medium of the device. You have to either be an acid or alkaline media typically in order for the efficiency of the device. So if you look at the number of photocatalysts that we had at our disposal in those days, we had the sort of semiconducting family and we have the oxides. And you can see that the semiconducting family does pretty good on the electronic structure requirements, the criteria number 1 and 2, but fail pretty badly on the stability criteria. They tend to either dissolve or form a passivating layer. So we were looking to the oxides that did better on stability, but unfortunately had the wrong band structure. The oxygen P states tend to be too low. So we say, okay, well, maybe we can find some outliers. Maybe we can tweak the electronic structure, but keep that stability that we really want it to be. So this is an early version of the materials project, and we decided to only focus on chromium, manganese, and vanadium-based ternary oxides. And we did the first screening of the materials project. We screened for phase stability and band gap using a functional PBE plus U, which is not perfect, and we know that. So we have a wide, generous span for that band gap, because we know we tend to underestimate it. Now, all that data was already available. That goes back to like what you've already calculated now can come and help you in other studies. So we hadn't done a single calculation here yet. Here we started, and with 400, we started doing new calculations. Now we use a better functional to refine that band gap a little bit. And then eventually we use band edge energies, which are also quite hard to calculate. Stability in water, the Courbet diagrams that we were developing through the Duracell project. And out comes the magic number 34. 34 possible candidates. But I really want to highlight this part here. We didn't have to do anything. This could take seconds today with the API. So we were very fortunate that we had partnered with John Gregoire, because he had inkjet printing combi synthesis techniques at his fingertips. So these 34 known phases that pass the computational criteria, he made 17 of them. That's pretty impressive. I have very few partners that can make that many different materials in a short amount of time. But maybe what is exciting also to see here, that 16 of these 17 phases actually showed OER current. So they had some sign of life. And we could also couple that to functionality and insights about the electronic structure of these materials. We saw that through the amount of photocurrent, so the larger these circles are, correlated with the amount of vanadium 3D band character at the conduction band minimum, and minimizing the amount of oxygen character at the valence band maximum. So it gives us design insight on where to go and look for others as well. To give you a sense of the impact of this, not just one work, but the years that JCAP worked on photoanodes, here's the evolution. I think John made this survey in 2020, where the amount of photoanodes that we had discovered through the literature, and these red and blue, red and green additions there, that's all through high throughput computation and or experimentation. That sort of adds to the candidates of photoanodes that are possible for water splitting. So it really has an impact on materials discovery. So fueling the fourth paradigm in terms of the machine learning aspects. I'll take one example. So this is one of the earliest data sets that we developed. Together with Mark Gasta, we developed a workflow for calculating the elastic tensor. And you might think that, oh, that is a really old-fashioned boring quantity. Why on earth would we be interested in that? Turns out that the elastic tensor has a wealth of information that people can use in different varieties, and I'll show you. So my student and his student, they were very excited about this. Of course, even those days, Twitter was more positive in those days. Here is the data that we published in Scientific Data, charting the complete elastic properties of inorganic crystalline materials. We started out with 6,000. I think we now have 14,000 calculated tensors. Compare that to the 200 we can find in the open literature. So this is truly a significant change in the amount of data. This is a paper that was published in JACS some years later, where they used the machine learned version of those elastic tensors to identify materials with high hardness. A group that had nothing to do with us, but they used our data to machine learn high hardness and made these materials show through Vickers hardness tests that these were indeed hard materials, rhenium and I believe tungsten materials. And here's another example, same publication. Now we have 12,000. We have 2,000 bulk and shear moduli and 12,000 band gaps that went into the machine learned version of Debye temperature and photoluminescence estimates. So people came up with new phosphor materials. So what I'm hoping to show here is that by calculating these fairly fundamental materials properties, other groups take them, leverage them as an innovation multiplier, and go off and do exciting discoveries of their own, which then turns out to be in Nature Communications and JACS. So the discovery aspect compared to the data computational aspect. This has really exploded in the last couple of years. The amount of machine learning that's done on the materials project, not just these sort of what I call funnel, where you filter for certain properties, and occasionally you have a loop that goes back and machine learns things, but also taking our algorithms. The Open Catalyst project used almost all of the materials project infrastructure to accelerate their discovery and their data sets on surfaces and absorption. Google DeepMind, that published in 2023 in Nature, also used a lot of the machine learning, the data and software infrastructure of the materials project. And I'm listing just a few other things here, where it's X-ray absorption spectra, NMR, automated labs. All of these are using what I would call NP inside. It's a little joke. They have either the algorithms, the data, the software, and some aspect around them to accelerate their work. One thing that I had not anticipated when we started was that saving some data that you don't really know if it's going to be useful may actually have a tremendous amount of value. So we saved every single relaxation of all the crystal structure that we did, mostly because we just wanted to show people that, hey, we actually found a local minimum, so that they would build some faith in our data. But it turns out that those relaxation trajectories were then a gold mine for when people started doing what we call the intra-atomic machine learning potentials. So these are now trained on the enormous amounts of energy and force data that we still have in the materials project. And all of these that you may have heard of, M3GNet, ChargeNet, Maze Foundation Model, they're all trained on this data that we have saved since 2011. And if we hadn't saved that, I guess that this revolution would have happened later. Here are some examples. In particular, the Maze has a very impressive range of applications, from doing Probet diagrams, surfaces, and here is a solid state battery interface that you can actually see passivating quite nicely in a few nanoseconds. And that's all done now, getting quantum accuracy through longer timelines through these potentials. So I'll just end with the aspect of democratizing materials data and that aspect of it. This is the Materials Project website. It's also something that we keep innovating and refining. It's not static. If you look up a particular material, here cadmium telluride, if you look at the number of apps that we have, I'm particularly excited to show that we are getting more and more contributed apps. It's not just data that we produce in-house, but also other people in the community that are coming to us with large, wonderful, what I would call gold standard data sets that doesn't exist anywhere else. And say, we want this to be on the Materials Project because we have a large audience and this is the right place to put the data. So we have the Synthesis Explorer from Olivetti and Sater. We have the Catalysis Explorer from the Meta collaboration of Facebook. And we have Andrew Rosen's entire MOF data set from his PhD that he spent a lot of time on helping us to curate. I have already noted that we have put a lot of effort into not just calculating crystal structures, but also properties. So you can see here a trajectory of all the different properties, or at least the larger ones, so the majority of the ones we've calculated since 2011. And you can see that the number of crystal structures is actually fairly small in comparison. It's mostly the properties that we keep growing. And every single property needs a fair amount of attention. The number of papers that are citing the Materials Project, I have to look this up every day because it kind of changes, but I think today it's 5 papers per day are published right now citing the Materials Project, and 2 of them are on machine learning. And that has rapidly risen in the last couple of years. So that also gives you a sense of how excited and data hungry our community is. And I'm very, very happy that we were inducted as a pure data set by DOE, going above and beyond the standard requirements and acting as community leaders. This was a true honor for us. And we're happy to be part of that fabulous family of data curations. Maybe also to give you a sense of how the Materials Project keeps rising in interest. So we're comparing here to 2 other databases, K-Base, which is in another space, is in biology, and OQMD was started as about the same time as the Materials Project. And as you can see, since 2021, we are steadily rising according to the Google scientific interest metric. We have over 500,000 registered users today, and most of the world is logging into the Materials Project on a daily basis. And as Linda noted, more than 300 new registered users every single day, handling 215 million API requests in 2023. So with that, I'm just going to summarize and outlook, and I'm very happy to take your questions. I think it's a very exciting time to be dealing with data and machine learning. And I think it's we have to recognize that data is a tremendous innovation multiplier. Value, the fuel. What are we going to do with it? These things are expensive. A highly curated data sets are very valuable. They need organization and curation and featureization to be valuable. If you just drop it in Dropbox somewhere, they're not valued that much because nobody will know them. How much do we value that they stay in the public domain? How much do we want them to be accessible to all of our scientists across the globe? And I will say, as somebody who has now for many years had this group of interdisciplinary scientists that have 1 foot in software engineering and 1 foot in material science, that is not a bad place to be. I can't graduate them fast enough. People call them up when they're sitting at their benches and want to hire them. So with that, thank you so much for everything, for your support over the years, and for the partnership.
Questions from the audience? Matthias?
Yeah, I just like a thank you for this beautiful overview of this long history of the Materials Project. And I'm wondering, so it looked very simple, the workflows that you showed. They look just a few diagrams with some boxes in there. Is this where the meat really is of making this work? Is this developing all these sophisticated tools, and I want to call them algorithms to some extent, that go into this process?
So that's
Or is it at the end just the output, the calculation that we do this?
So maybe you could repeat the question because we're
right.
having a problem with that.
Yeah, so the question is, if the workflows are as simple as they look from an illustration, or what else goes into the software development? So it's certainly the first part. If a student comes to me and says they want to do a particular exploration, you first go and see, do you have the data for that? And if they don't, they have to develop that workflow. And that workflow is something that will take them a while because they have to sit now, figure out automatically what parameters to use. If it's an insulator, that has to work for insulators, semiconductors, metals, whatever, right? So you have to pick the right parameters in the Schrodinger equation. That has to be done automatically, but it usually isn't. That's one of the first parts. And then you have to see all these parameters then reproduce what is known from gold standard experimental data sets. And if they don't, you have to go back and tweak it. So it's a lot of fine tuning of those boxes and figuring out how do I automatically choose the right parameters because I can't have students do it. That takes a long time. So even though it looks simple, the actual tweaking of the decision makings can be quite time consuming. Then after that, after the workflow, then comes the builders. And you saw the builders, so if we do a new property, it has to come with a new builder. It has to come with API endpoints. It has to come with a web-based design if it goes on the website. So there are all of these aspects. So if you want to follow a materials property all the way, and I have had some students who've done this, and they have all said, oh, there's a lot of work. I had no idea there was so much work involved in this. That answer your question?
Yes, it does.
Yeah.
And but it's not one graduate student following
Oh, no.
5 years, no?
Well, actually, I have a few examples of a few have done that. Yeah, they followed it all the way, and they're quite excited when they come to the end.
There was a question.
So I think, is a question in three pieces, right? The first one is definitely when you're generating data, taking into account of the uncertainty that you have on the data is very important. And the way in which I think to a discovery process is to find singularity in a vast chemical space. And those singularity may not be easily reachable with interpolation schemes because you need to have something that is outside the box, right? Something weird. And the next step is, and then maybe you need to improve on Ph.D. in order to get those singularity. So how do you see the future of the material project in this direction?
Yeah, great questions. I have to, okay, I'm gonna try to remember this. Okay, machine learning is a homogenizing mean field thing, so you're not gonna get the singularities quite easily. DFT also comes with issues, and how do I think that I'm gonna improve this going forward?
And uncertainty.
And uncertainty, yes. So absolutely, when we build our phase diagrams, to give you an example, we looked at an experimental ones, the one we can compare to where there is existing data, and when we calculate the elastic tensor, we published the first data set saying we can reproduce what is known from experiments with a plus minus 15%. So we already from the beginning, with the first workflow, decide how well do we do. But that incorporates also that there is actually experimental uncertainty as well, right? So if we found two different measurements of the nickel oxide elastic tensor, it turns out that was more different than 15%. So we have uncertainties both on what I would call the gold standard experimental side, as well as on the DFT side. The best we can do is be aware of it, as far as I can tell. And as soon as we get better methods from DFT, we try to incorporate them if they are amenable to high throughput. That's number one. Number two, on machine learning, you're absolutely correct. It's an interpolation scheme. So you might miss very, very sharp discontinuities in some. But that's something that we will have to figure out together. The materials project isn't going to do that alone. We are going to try to supply as much data and knowledge and best practices as we can, but the community has to be our partner here. We cannot do that alone.
There was one more question inside.
It was a question along the same lines, but not as expertly asked. And that what you call data really are calculated quantities. And I was wondering what kind of verification you have that it is really accurate. And you started speaking to that just now. You said there are only like a couple of hundred measured quantities. You have hundreds of thousands of calculated ones.
That is
So that's a terrible mismatch. So
absolutely. I could not agree more. And this is why occasionally when I show that slide with all the elastic tensors, is to some degree, here we go, here be dragons, right? We don't know that we are going to be correct in chemical and structural spaces where we don't have a single experimental verified data point. We can only trust in the systematic accuracy or inaccuracy of DFT. That's all we've got. So I have been saying for the last couple of years to anyone who wants to listen, including philanthropists, gold standard experimental data sets. using robotics and automation to get those maybe, so we don't have to send the poor graduate students in there to do really, really boring, horrible work. That is super important so that we can together explore the space and be better verified to make sure that, and to also challenge DFT to make sure that we're doing the right thing. Because if we have experimental data points that we trust, then if we don't get the right answer from DFT, we can improve those methods. So absolutely.
So, question.
Time is spent curing standard data on a weekly basis. Do you do research? How do you do research? How do you develop the data? And also, on the DFT calculations, that the temperature dependence, so do you just assume?
So the first one, how much time do we spend curating? It's hard to put a number on that because sometimes we have a bit of a campaign when we have new data coming into the materials project, and then we spend a fair amount of time looking on phase diagrams, seeing it. So some of the things I showed very briefly, we get reports out when we have a new build that's being built, and we have a sort of a beta version that we're looking at, and we get, oh, we've broken a hull of one phase diagram. Let's go and look at that. Does that make sense? Should we have broken the hull? Are we suddenly destabilizing a binary that we know is stable? That's a problem, right? So then we have to spend a lot of time on it. Sometimes it's really just, if you're not importing any new data, then I would say the curation is honestly mostly us looking at it from a functional perspective and our users looking at it. That's the beauty. We have a discourse page where all of our users are maybe 500,000 of them are that active, but a fair number of them are fairly active. And they will tell us, hey, I think you're going to get this very off here. You really know what you're doing. So we do get the help of the community, and that's really valuable. So that's on the curation side.
And then the temperature dependence.
Temperature dependence, right. So do we do temperature dependence? Not per se. We do run DFT, which is 0 Kelvin. When we do phase diagrams, we can add a machine learned variety of the vibrational entropy, which we will do, for example, when we do synthesis exploration. But our phase diagrams as they are presented are 0 K.
Okay, and then my question is then how do you relate that to experiment?
Right, so we typically enthalpy formation is the one that we look at when we compare our formation energies to the experimental data. I still remember I did type into the test in the early days of the Materials Project to make sure that we got all of that benchmark. And we had to incorporate, and we still do, what I would call a DFT correction scheme, because some things like peroxides, superoxides are not well characterized in DFT, so you have to include the correction term to even get promoted to the right phase diagram.
All right, we have an online question or two.
Sure, we have a few. Okay, we had a couple that were actually kind of similar, so I'll read both of them. The first was, what is your biggest learning from developing curated databases that you can share, which others might leverage for developing similar databases in other spaces? It's a similar. What do you think goes most into seeding these new developments? The technology, the expertise, the maintenance, the costs, et cetera. And how would you? What advice would you give to someone starting out now that you've been doing this for a while?
First of all, I think don't be afraid. Just any start is better than nothing. So I think it's very easy to get overwhelmed when you're taking on a large task. And even just getting in there and doing it is better than not doing anything at all. That's number one. Number two is this has taken a tremendous amount of interdisciplinary effort. So having an early appreciation for the need for robust programming, the need for version testing, the need for that aspect of the project. And I was very fortunate the early people that were part of the project, they all had that mentality. So we all started out that way rather than thinking, we're just going to produce a bunch of data and give it to the public, right? That easily becomes a large flat file of text that sort of ages and doesn't do very well. So having that ambition from the beginning and building that in was crucial. Long-term support from DOE, I cannot thank you enough. That was crucial, and if without it, we would not be here today. And having the faith in us that we could do this, and letting me grow this interdisciplinary team of software developers. I think I had a picture of them on the last slide there. That almost all of them, here they are, standing outside of LBNL yesterday. These are full-time software developers, and with most of them with a material science background. but have now become almost full-time software engineers, but they still have that dual interdisciplinary focus, which really makes them unique in this space.
Okay, so I have a different question that sort of hits my heart. You touched on superconductivity. This is a notoriously tough materials problem. I'm just reading the question.
Yeah.
What do you think is the future of machine learning and AI for superconductivity?
Ooh, that's a great one. Okay, so first of all, it's not my topic of expertise. So my understanding is that we can calculate what classical superconductivity, like you know, the one that is traditional superconductivity rather well, the one that has to do with electron-photon interaction. So that one is doable. When it comes to the cuprates and those more complicated systems, we will either need a lot of data or a robust theory that tells us exactly what interaction parameter we need to calculate before we can expand that. And I'm not, to my knowledge, we're not quite there yet. It's not my field of expertise.
I knew it was a tough question.
Victoria?
So I wanted to ask, how difficult is it to integrate outside data into the system? I think you've done it with a couple of kind of key partners. That's kind of part of my question.
Yeah, so we are working on making a number of different varieties of that kind of incorporation. We recently launched something called micro contributions, where you can just contribute one stellar data point if you have one for a particular material, and it would literally only take you like a few minutes. And then my staff is just going to look it over to make sure it isn't, you know, it's okay. But yeah, that's super simple if you're logged in. Then if you have these larger data sets and you want an app with it. So also my staff is working on a version of like a contribution portal is already there in the materials project called MP Contribs. You can send in a small data set, you can send in 20 data points, you can send in 10,000 data points. But if you want those 10,000 data points to become an app, like some of the ones I showed for the Moth Explorer and the Census Explorer, then we have a framework for people to work with us on that. We can't do that all alone, and we probably shouldn't, because the people who own the data, who made the data, are the experts on how that data should be used. So we'd like them to be part of the process. So we will happily work with them, but they're going to also have to sort of come to us and say, hey, I have this great data set. Will you work with me? And we will happily do so.
And is there a way to identify kind of the key experimental data that kind of would make the models more robust or better performing?
I think there's absolutely in different fields and different applications. I think that's eminently doable, and I would love to be part of conversations like that.
So the particular project is not the only player in the Hypercube community. So since the beginning, there were many database and there was a healthy competition. I want to know your impression and if the competition was good or not, or if you have alternative where the competition could be avoided at some synergy period.
Oh, that's a good question too. So first of all, I've been long enough in America. It's like competition is always good, right? I mean, it is, and I think also high throughput computing in itself has been. Anyone today can do some amount of high throughput computing. The question is if you have the ambition to become like a data provider and build the analysis tools that come with that and that whole aspect of the materials project. That's not everybody's ambition, right? Some people just want to, here's the data I produced, here it is, take it or leave it. It's kind of up to you. That's perfectly fine. No problem with that. I do think going forward that we are now at this crossroads to some degree. We have a data management plan that we ask from our PIs, most of us. Like, where are you going to put your data? I think it would behoove us to have at least a few blessed places where we decide here's where you should put your data. Because if it ends up being in everybody's backyard, then it's going to be much harder for us to organize and become accessible and amenable to the machine learning world. So I don't think there was any problem with it in the beginning, but I do think it would be a good thing for us to just like a protein data bank, find a few places where we can curate and keep track of the materials data that we are producing today. The gold standard data sets. Oh, a little is better than nothing. That's always gonna be my.
So we have a couple of additional questions. Kate.
I'm just curious if you have comments thinking about from an experimental point of view from other fields, like. I think one of the major challenges which you touched on is quality of data and having the kind of data you can build these AI models on. And I'm wondering if you can comment sort of more generally beyond materials. Are there principles that we as a scientific community need to be thinking about as we're developing data management, as we're communicating with PIs about making data available? Like, what are the core pieces of information that maybe are universal across different fields as we move forward into this work?
Across different fields, that's a tough one. I mean, so obviously, right, there are parallels. If you look at the biology field, the protein data structure, like it's a structure, we have structures in materials and we have structures in molecules. And so that's the baseline. But then it comes the properties. How many of the tiers of properties? Where's the metadata for that? And in terms of materials, it's all about the processing too. How do you actually make the material and the varieties of it? Is the property depending on whatever length scale you're measuring? I think that every field should at least figure out what is the minimal amount of data that would make sense. I also think that people who publish the data that goes into the paper should at least be somewhere accessible or at least connected to another data point. I think one of the problems with how we do things today, we drop it in a Dropbox somewhere, but it's not discoverable. It doesn't even have a link to the paper that data sat, and it just sits somewhere, and probably the PI knows what it is, but that's about it. So, like, the student knows. So, building out our requirements of how accessible or how the linking between data points, I think is maybe more important than exactly what data. Because I think that for learning from, for example, the biology field, talking to those people who've been doing this for longer than we have, they say that, you can see which data sets are valuable after a while, because they are those data that are so expensive to regenerate that people will keep going back to them for benchmarking, for verification. And you're going to see that on the sort of usefulness. And that's why I bring up the use of the Materials Project all the time, not the number of data points or whatever, because I think the usefulness is what actually shows you what the value is, not how many there are, how many terabytes, how many this and that. It's the fact that people keep coming back, they trust it, they use it over and over again. So I think building in how much people use the data into what you're going to store, like you start out with storing most of it, but then as things don't get used, maybe they end up in glacial storage. And they may be accessible, but it will take a little bit longer time. As long as we have the links, we can find it. That would be my principle. Did that come out reasonably understandable? Sort of thinking as I talk here.
Thank you so much for giving a wonderful talk. I was not familiar with anything that you gave. I'm an inorganic chemist though. And so what I was wondering about is that you keep a lot of data, right? So you guys keep the majority of what you do. What happens when someone submits information that's different than what you guys I guess what you guys computed compared to experimental? Do you keep that as well? I know that you probably update your database, but do you keep that information and is it accessible to the users?
Yes. Yeah. So especially given that we know that some of our methods in DFT have different flavors of accuracy. So I'll give you an example, the band gap. We typically calculate the band gap with PD/U or R2 scan, but I have people have contributed band gaps with other kinds of functionals, and we just list those two with the sort of tag. Here's another functional, and here's the band that we get with that. And I think the value of that is that if somebody comes who doesn't know that, they go, oh, here are a number of different techniques that they measured, calculate the band gap with. Maybe somewhere around that is the right number. It gives you some sort of intuition of the error bar. Yes, we do. Unless we can find out there's a significant something wrong with either our calculation or their calculation, we list them together with the right metadata so people can make a decision.
So to close the session for these ceremonies, we've asked some standard sort of fun questions. So one of them is, what initially drew you to a career in science and especially material science specifically?
Okay. At the risk of oversharing here. I grew up with two academic parents, one in comparative literature and one in biology. So there were endless discussions at the dinner table because my mom was in comparative literature. So there's like nothing really sort of gets to a point there. They just keep on arguing. Whereas my dad was much more, well, here's the answer, here's the fact. And I, as a person, got more drawn to that. I also ended up spending a lot of time, he was a field, he was an experimentalist, and he made population dynamics of little clams in the Baltic Sea. So I spent my summers tagging little clams with their like moving little numbers on clams. And I had a good time with that by the coast, so who wouldn't have a good time? I think the combination of my natural impatience as a person and the fact that I had a good time hanging out with my dad was probably the early reasons. Material science, though, that's a tough one because I didn't know. I did my master's thesis on neutrino oscillations, and I thought that was really cool. So as a PhD, I kind of at that point knew that as long as the topic wasn't some sort of physics, chemistry, I loved quantum mechanics. So I interviewed 4 different professors in 4 very different fields: optimization, mechanics, relativity theory, and material science. And you know why I chose material science? Because I like the people best.
Was this your graduate work?
Yeah.
Well, we won't overshare. Very cool. So another standard question that we ask is, what impact has involvement in the National Laboratory had on your career?
Well, I am really, really happy. I was hired first as a staff scientist at the National Lab and only became a professor later, because I don't think the materials project would have happened otherwise. I'm actually fairly certain it wouldn't. Because at the National Labs, there is this atmosphere of team science. We are supposed to do things together, solve big problems, and we can also hire long-term staff. And the materials project requires all of those. And they also required us all to come together and sort of say like, okay, we're gonna solve this big problem together. And none of us are gonna walk away thinking that, oh my God, this is not just CS or not just material science, it's really an interdisciplinary baby and we all take pride in it. So yeah, if I'd been first hired as professor, it wouldn't have happened. So that's really grateful for that.
And the last of these questions, again, that we've asked for is, what advice would you give to an early career scientist?
Oh, today.
Today.
Today, they all run off to start companies in my group. But if they want to be a scientist, well, first of all, I really think that from my own experience, that following your heart is really important. Follow your passion and your heart. And even if you end up with some bumps in the road, and we all do for various reasons, family, moving, difficulties, I've had the most torturous way towards where I am today. So I would say that it's worth it.
Great. Well, let's thank Kristin. Giving my humorous comment is that we will get you a bright red battery to put with your car and gasoline.
Yes. Yes.
Yeah.
I have been thinking about that. But it's a little, yeah.
And of course, we have to say some other additional thank yous. First of all, thank you to Basic Energy Sciences, both for supporting Kristin for all these years, but also for helping with all the organizational aspects of this event. So thank you very much to Andy and his staff, especially Carrie, Carrie isn't here right now, but she was a lot of it. Our office, the Office of the Deputy Director for Science Programs, also has a lot to do with this, but most especially Katie Schwartz. So, and of course, we have the Communications and Public Affairs, who is always behind the scenes and making all these activities function as seamlessly as they do. So Thank you very much, Allison. So it's been great having you, Christine, as always. Thank you very much. Let's give Christine one more round. Thank you. Thank you. Thanks to everyone.